In this video, we are going to discuss how to calculate energy in simple harmonic oscillations for an oscillating spring. Here you have a 2 kilogram mass attached to a spring and displaced 8 centimeter from the equilibrium position. It is then released and oscillates with a frequency of 4 Hz. We need to find the energy of motion when the mass passes through the equilibrium position, and what is the speed of the mass when it is 2 centimeter from the equilibrium position. So here we have a spring that has a mass of 2 kilogram attached to it. And initially when it is in equilibrium position, we can write x as its position to be equal to 0. It is then displaced by a distance of 8 centimeter. So let's say it is stretched by 8 centimeter. And we can call this as the amplitude A because this is the maximum displacement the spring will have. We need to find what will be the energy in the spring when it comes back to equilibrium position. Now, when the spring is stretched or compressed to a maximum displacement, all of its energy is the potential energy. So we can write the energy of the spring as only potential, which is also equal to the maximum energy of the spring. And this maximum energy E can be written as half k A squared. As the spring is released, this potential energy now gets converted to kinetic, and at the equilibrium position, all of the potential energy is now converted to kinetic energy of the spring. So the energy at equilibrium position is just kinetic energy of the spring, which is equal to the potential energy stored at maximum displacement. So we can write this to be equal to kinetic energy, which is the energy at the equilibrium position. So let's solve for this. This will become half k A squared. We know the amplitude A, which is 8 centimeter, which you can also write as 0.08 meter. But we don't know what is the force constant K. Now we can solve for K by using the relationship between frequency and force constant. We know that omega is square root K over M. So now let's take square on both sides. Omega squared becomes equal to K over M. Multiply with M to solve for K. K becomes equal to M omega squared. Omega is nothing but 2 pi F squared. Now substitute. Mass is 2 kilogram. 2 pi times F frequency, which is 4 Hz squared. That will give you K as 1262 Newton per meter. Now let's substitute the spring constant in our equation here. We get K to be equal to half. Spring constant is 1262 and A is 0.08 squared. That gives you the energy at equilibrium position to be equal to 4.04 joule. Next in part B, we need to find the speed of the mass when it is 2 centimeter from the equilibrium position. So we need to find its speed at a new position. Let's call it x1, which is at a distance of 2 centimeter from the equilibrium position. That's around 0.02 meter. And we know the expression for speed v. It is square root k over m a squared minus x squared, where a is the amplitude and x is the position where we are finding the speed. So in our situation, x right now is equal to x1. So let's substitute again. Square root 1262 over 2. A is 0.08 squared minus x is 0.02 squared. That gives you the speed at that position to be equal to 1.95 meter per second. Next question. The mass m shown in the figure is displaced a distance x to the right from its equilibrium position. First part of the question is asking us what is the net force acting on the mass and what is the effective spring constant. So here in this question you have a mass m which is attached to two different springs having different spring constant, and it is displaced to the right by a distance of x. When it is displaced to the right, the second spring is compressed and the first spring is stretched. But the displacement in both spring remains the same, which is x. So here the force experienced by each spring will be different, but they will have the common displacement x. So we can calculate for the first part of the question the net force F to be equal to force on spring 1 plus force on spring 2, which will be equal to K1x plus K2x. When I'm calculating the magnitude of the force, it's okay to not take the negative sign here because the negative sign only indicates that force is going opposite to displacement. So we get the net force F as K1 plus K2x. So first part of the question is done. They are also asking us to find the effective spring constant. This term K1 plus K2 over here is K effective. So we can also rewrite this as force equals K effective x. K effective to be equal to K1 plus K2. This is the effective spring constant. Anytime two springs or multiple springs have the same displacement because of a single mass, K effective will be just sum of individual spring constant. Now in part B, they have given you the value of K1, which is 100 Newton per meter, K2 200 Newton per meter, and we need to find what is the frequency of oscillation when the mass is released. Now frequency of oscillation F can be given as omega over 2 pi, which is 1 over 2 pi square root K over M. And K here is the effective spring constant because you have two springs in motion. So I can write this as 1 over 2 pi square root K1 plus K2 over M. So let's substitute 1 over 2 pi square root K1 is 100, K2 is 200 over mass M is 10. When you solve this, you get the frequency F to be equal to 0.872 Hertz. Now part C says, if X is 0.1 meter, what is the total energy of the mass spring system after the mass is released? And what is the maximum velocity of the mass? So if X is 0.1 meter, that will be the maximum displacement of the mass because this is how much I am stretching or compressing the spring. So you can find the total energy E as half Ka squared, where A over here will be the value of X, which is the amplitude, 0.1 meter. K here will be K effective, and I can write A to be X squared, which is half times K effective is 100 plus 200, which is 300 times 0.1 squared. That gives you the energy to be equal to 1.50 joule. Next, we need to find the maximum velocity of the mass. Now, maximum velocity you can find when the kinetic energy is maximum, and maximum kinetic energy is at the equilibrium position, which is equal to the total energy. So we can write K to be equal to E, or half mv squared to be equal to E. To find velocity, I have to rearrange the terms. So we multiply with 2, divide by m, and take the square root of the whole term. So v becomes equal to square root 2e over m, which is square root 2 times 1.50 over m, which is 10. That gives you the maximum velocity to be equal to 0.548 meter per second.